Hey, welcome back to the shop. This should be part 4 of the Powerfeed project. As you can see, I have the Powerfeed right now mounted to the milling machine, and I'm figuring out how much travel I need to engage and disengage the clutch. And oops, I hit the lamp. I have this groove in the clutch, and there will be a lever engaging this groove and moving this clutch piece around. But I need to know how much travel the lever needs, so I have a gauge block stacked that fits right into this groove. Then I took a small square, I butted it up against it and made a scribe line over here. Then I disengaged the clutch. This is still a bit hard to move as nothing is really aligned, and I aligned my square again and made another scribe line. And now if I take a scale, I can measure from one to the other scribe lines, and I know the distance, the travel that I need. And it's 13 millimeters. It's from center to center, it's 13 millimeters. So, and also these are the positions that where I have to shift. These are the actual position will not change anymore. Now I figure out how to make a lever mechanism to accommodate this movement. I figure something out. I'm going to use this piece of cold rolled steel, might be carbon steel, and I already faced it down to length, and this fits exactly on top of the clutch housing. I will machine out a slot and a pocket on the back in which a slider will run, and the slider has a pin through it, and this pin will move the clutch, and on top of this plate will be a lever engaging this single pin. So let's go to a milling machine and make this piece. Mill out the pocket and the slot through it and see how it goes. Okay, I put the part back in the vise, I touched off the edges, and now I'm about to hog out the slot in the middle, and I'm going to pre-drill the end so I don't have to plunge down with the end mill, which end mills don't like very much. So let's drill them out. Okay. Next thing will be to come back with an undersized end mill, hog out the slot. I want the slot to be 6 millimeters, and I'm going to plunge with a 5 millimeter end mill, or to rough out. Okay. roughed out the slot. This end mill was barely long enough to go through all the way, but it worked. The slot doesn't need to have exactly 6mm. This is a clearance slot, but I still want the sidewalls and the ends to be nice and clean. So I'm going to plunge down on each end with the 6mm end mill. And now I can mill out the material in between. I'm taking pretty light passes so my end mill doesn't get deflected. Okay, machined a nice slot in there. Now we hog out the pocket on the underside. With the same end mill, yeah. Okay, as you can see, I roughed out the pocket with the full depth of cut and pretty small side engagement of the end mill, and that works out very well with when you have to remove a lot of stock. It's, in my mind, more efficient than taking shallow passes at full width. And now we do a finishing cut, two finishing cuts. Okay. Best invention ever, the vacuum cleaner. Okay, I have the cover plate here with the slot and the pocket hooked out, and I drilled it in 4 corners so I can screw it on here later. And I also made a brass slider that goes in here, and there's a nice close fit, and we will make 2 bars left and right of this pocket that will hold this slider in place so it doesn't fall out like this, but still allow it to slide around. And we will just cut these strips from cold rolled steel, machine them to length, drill them, and drill and tap this blade too, so everything can be screwed together. Okay, I made these parts off camera because it's just sawing off stock, facing it to length and drilling. But here is the clutch actuating slider hold plate thing. There is the brass slider inside the big plate. It's held in place by these 2 gibs, and there is a 5mm pin right through it, and that's what engages the clutch. And now we go to a milling machine and I'll show you how this all will come together eventually. Again, I have set up the Powerfeed on the milling machine. Now I have to fill this in. Or is it the other way around? Yeah, this is the right orientation. Now the pin is in the groove of the clutch. And as there are no bolt holes yet, I'm just using a Bessie clamp to hold everything together while we test it. Now the clutch is engaged, and if I push this pin over, now the clutch is disengaged and I can crank the table very easily. But if I push the pin over, oops. Now the clutch is engaged. I can't crank the table, or in fact I can crank, and it drives the motor through the gearing, but it's pretty hard to turn. So the clutch makes sense. So this is disengaged, and yeah, nothing is aligned yet, so it's a bit hairy to get the clutch back in. So now it's, and the coolest things of all is that we can test drive it again. Let's hook up some power to this motor. And give it some and it's cranking along. Nice and quiet, and it pulls 1 amp. And I can stop it, and we can reverse it. I like it. Okay, I figured something out. I made this disc, it's just turned, center drilled, bore and reamed, and countersunk on this side, and we will screw it onto this plate behind the shifting pin here, so it can, and we will screw it down with a shoulder bolt, and we will machine a slot in here, and when you turn this, when this knob is turned, it will move and shift this pin, and that will engage and disengage the clutch. So next thing is to make the shoulder bolt. Okay, let's sketch out the bolt. We need a head, then we need a shoulder, and we need a thread. Let's draw in a center line. This is going to be a 5mm thread. This is going to be a diameter 6 minus 0.02 of a millimeter, and this is my counter bore is 10mm. So we make the head of the bolt diameter 9.5. The counter bore is let's do this proper. The thread needs to be, my material thickness is 5mm, but I don't want the bolt to go all the way through or even protrude, so we make it 4.9. Then we go up to the shoulder. We know that the shoulder needs to be 7.8 plus 4.9, that's 12.7. Oh, that's half an inch. And the overall length plus the counter bore is 4. Let's make it 4.5. So the overall length is 17.2. Then we need to slit it so we can fasten it with a screwdriver. 1mm, and that's a proper sketch. Everything there. And the way I did the dimensioning, I can reference everything off of this front surface, because first we're going to turn the shoulder, the long shoulder with the diameter of 6, then we're going to turn the diameter for the thread with a length of 4.9mm, and then we're going to part it off, turn it around, face it, and go to the milling machine and do the slitting. Oh, and of course, yes, we need some material for this shoulder bolt, and I think I'm going to use 10mm drill rod. Okay, you just saw me turning this shoulder bolt. Off camera I cut the slit on the milling machine with a 1mm slitting saw, and everything fits together quite nicely. So that's the shoulder bolt on which this knob will turn, and now we drill and tap the housing plate or the clutch plate so we can bolt this on. Let's take this plate off and drill the pivot hole for the actuating lever. I already machined the slot into it that will engage this pin. Of course I have to shorten this pin a bit, but this is the way this pin is going to be actuated. So let's take it off. And now we have to drill and tap this one hole. I touched off these edges and moved in my given numbers. Now we're just drilling and tapping one M5 thread right here. And I chucked the drill very short in an ER16 chuck. That means I don't have to center drill. And I don't have stub length drills, so this is my way to do it. Okay, and now for power tapping. There we go. Okay, we have the clutch plate here with the shifting pin, and here you can see also the two gib plates that hold the brass slider in place, and we have the actuating knob here with the shoulder bolt which goes through the center bore, and we drop the slot onto the pin and screw that thing down. Now we should be able, yes. As I rotate this knob, the pin goes side to side, and this will engage the clutch. Of course I will have to drill a hole here and put in a lever so I can actuate it nicely. This is a bit slippery to be the Powerfeed engagement, but it's working, it's running nice, it doesn't rattle too much, so far I'm happy. Now we go over to the milling machine, screw this plate down and see if it works there too. Back at the milling machine, and we have our clutch plate here with the pin, and now we have to make sure that this pin engages the slot, the groove and the movable clutch piece, and yeah, I hit it, and now we screw it down. And the alignment of the clutch plate itself is not super critical. There is a lot of tolerance in this whole construction. I also did not put pins in to register this plate against the housing because it's not critical. Just make sure it's flush on this side. Tighten everything down and give it a try. Oof. And of course this knob has almost no leverage for me. Crap. Okay, another time warp. Now we, as you saw before, I was not able to turn this knob by hand, as it was too slick. So I made the lever, and I need to solder this in. I'm going to silver solder this lever into this piece, and I used a screw-on plastic ball, and now I can nicely engage and disengage the Powerfeed. Okay. Finally, I got everything sorted out. I mounted everything up. I lubricated the clutch with grease and lined everything, and it's working great. At the moment, the motor is hooked up to my power supply, my benchtop power supply, and the motor is running, and as you can see, I can engage the clutch, and the table is moving along quite nicely. And at that speed, at 12 volts, the motor pulls about 1 amp. And the limit of my benchtop power supply is 1.5 amps, so the proper power supply I'm going to get for this motor will be a maybe 6 amp. 6 amp and a speed regulator for the motor too. But that's for the future. I'm waiting for the power supply to arrive, and I have to see which speed regulator I finally order. But so far this works quite nicely, and now my milling machine has Powerfeed. A lot of people mentioned in the comments why I didn't go for stepper motors, and I don't see benefits in using stepper motors for a dump Powerfeed. Stepper motors, in my mind, are only interesting if you want to position something in an accurate way. On my previous CNC milling machine, of course, I had stepper drives, which is the low-tech solution for a CNC. Better solution are servo motors, but as this only needs to crank to turn the screw until I decide to stop, the simple DC motor with a gearbox is a way easier solution. Also, some people commented that they want to use such an arrangement on the knee of their Bridgeport milling machines. I'm not familiar with the Bridgeport, and I don't know how hard it is to crank the knee. I'm not sure if the wiper motor is powerful enough to do it, but maybe look for Tom Lipton's solution, where he has just a hand drill with a clutch hanging off his knee. Of course, off the knee of his milling machine, not his own. That might be the easier solution and more reliable, because I'm also not sure how this motor will hold up to the use as Powerfeed, but I have 3 of these motors, so if one goes south, I have 2 more. Okay, finally a test cut here. I have a piece of rusty cast iron and a 6mm roughing hammer, and just for fun take a slotting cut through it with a 5mm depth of cut. Speed is 600 RPM, and we're using the Powerfeed, of course. so far. I'm pretty happy how this turned out. I hope you enjoyed this. This was a longer series. I spared a lot of the simple machining out. I didn't show a lot of the turning and stuff like that. Okay, I hope you enjoyed this longer series on the Powerfeed project, and thank you all for watching and commenting. See you next time.